I'll discuss the Cauchy's theorem on limits. First, Cauchy's first theorem and second theorem on limits. So this is the syllabus of Karnataka University BSc 4th semester paper 1. So sequences and series paper. So now let us see that statement of Cauchy's first theorem on limits. So if sequence an converges to a limit L, then the sequence action also converges to L, where that action is so that a1 plus a2 plus a3 plus so on plus an by n. So it means what action should be nth term of action is looks like this form. So now let us see the proof of this theorem, Cauchy's first theorem on limits. So let us take Bn is an minus L. Then Bn, then you can apply the limit on both sides of this Bn. So now see that limit as n approaches to infinity Bn, that equal to limit of an minus L as n approaches to infinity. So since this L is finite, so that the limit of constant is constant itself, so that this limit an can be carried that same term. So but this limit an is L as n approaches to infinity, so then this Bn becomes a 0, because since an is limit of an is L, so as n approaches to infinity, so that L minus L equal to 0 there. That implies Bn is 0 as n approaches to infinity. We called it as equation 1 there. So now let us take that here Bn is an minus L, so an should be Bn plus L. So now we have this xn is as given, so that xn is a1 plus a2 plus a3 and so on plus an by n. So then each term of a1 can be expressed in terms of Bn plus L there. So that we can plug in each term of a1, a2 and so on an. So then we have that, see that, keep remember L plus L plus L plus so on, that it means what? It is a n times of L there. So next you can take it to B1 plus B2 plus B3 and so on plus Bn there. So divided by L. So and then you can take that this term divided by L, and n gets cancelled each other, so that plus L. So then we called it as equation 2 that. In order to prove that this xn means what? It is the n term of an, so that we can take approaches to L, we wanted to prove that here. So it is enough to prove that this xn, because as we know that xn approaches to L, as since xn is in terms of that is Bn an plus this only, so then also enough to prove that B1 plus B2 plus B3 and so on Bn divided by n, which is also converges to 0. So now we can take a equation from 1, so that Bn approaches to 0. Therefore, given epsilon greater than 0, there exists a positive integer m such that Bn minus 0, magnitude of Bn minus 0 is less than epsilon by 2. That means modulus of Bn is less than epsilon by 2 for every n is greater than or equal to m. We called it as equation 3. Now again we wanted to prove that this Bn is approaches to 0 as n approaches to infinity. So then the sequence Bn is also convergent. So since sequence Bn is convergent, it is also bounded. So then this implies, so there exists a real number m is positive such that this modulus of Bn is less than m, means what? It is a boundedness definition for Bn. So then let us take this is equation 4. Now to prove that equation 2 Bn approaches to 0, so that let us take this modulus of B1 plus B2 plus B3 and so on plus Bn by n minus 0. So then we need to see that if you take a modulus of this numerator as well as denominator, so then we have there modulus of n is n itself. So then we have taken that. All intermediate terms of this b1 to bn is bm and bm plus 1 and so on bn plus bn. So then we have, since for every n is belongs to natural number capital M, that implies modulus of n is also n itself. Therefore, that imply that less than or equal to 1 by n each magnitude of this each term of bn. So then we have, as we know that this is a m plus this is m and so on m times of this one, and plus this is what we have taken, that is the epsilon by 2 and so on m minus n minus m times of that. Using that from 3 and 4 we need to have this term here. So that is, as we know that this is m times of capital M and this is n minus m times of epsilon by 2. So then, which means that this is what we have there in the left hand side. So then we have taken that n by m, m by m times of capital N, n minus m by n times of epsilon by 2. So it means, keep remember there, m by minus m by n and plus m by n gets cancelled each other. So then we have there m times of capital M by n. So then this is what we have, epsilon by 2. So because this n minus m by n is 1 minus m by n, that should be again it is less than n 1. So that's why we can have there m times of m by n plus epsilon by 2. But as we know that m into capital M by n is less than epsilon by 2, if provided that this reciprocal should be less than 2 by epsilon. That means if n is greater than 2m capital M by epsilon, if p is a natural number greater than 2m m by epsilon and q is maximum among m and p, then we have there, so that just we can replace it here in that, so that this means this is epsilon by 2, again it is also epsilon by 2 for all n should be greater than or equal to capital P. This means it is epsilon, and then it means it is a definition of boundedness, so that limit, so then we can, this approaches to 0 there, or it converges to 0. So then from equation 2 we can substitute, as we know that this is xn is b1 plus b2 plus b3 and so on bn by n plus n. Xn as approaches to L means it converges to this limit as n approaches to infinity, because as we know that it is a 0, that only thing it is a L remains there. That means it is which contains only a1 plus, because which we have that term bn is also a term of in terms of an, so that a1 plus a2 and so on plus an by n as approaches to limit. So converse of this theorem on limits need not be true, because if you take it that suppose if it is 0, so that it doesn't converse part of that limit, Cauchy first mean value theorem on limits need not be true. By considering that we have that an is alternative terms of that sequence, so then we can take it that this an a1 plus a2 plus a3 and so on plus an by n, if it is 0, if n is even, because since every time it becomes that as n approaches to even term here, so then it is a 0 there. And then if it is odd, then it is a minus 1 by n there, so that as n approaches to infinity this becomes a 0. So but this is a divergent, so that's why converse of this Cauchy's first theorem on limits need not be true. Therefore limit of an as n approaches to infinity is L is not always true. So now let us take that second theorem on Cauchy's second theorem on limits. That statement of this theorem is sequence, if sequence an of a positive terms, then limit of an power 1 by n as n approaches to infinity is limit of an plus 1 by an as n approaches to infinity, provided limit on the right hand side exists whether the finite or infinite. So in order to prove that this theorem, it is given that the right hand side given limit exists which is finite or infinite. We consider the two cases. One is limit of an plus 1 by an equal to n, where L is finite. Then we are taking the definition of limit so that we can write it this way: modulus of an plus n 1 by n minus L as less than epsilon by 2 for every n is greater than or equal to m. So then we can, this means what? It is an plus 1 by n lies between plus and minus term of this L. So then put n equal to m plus 1, m plus 2 and so on, n minus 1. We have taken that here. So already we have that m plus 1 by m, and then we have take that up to that this term, and then we can multiply all the terms n minus 1 inequalities. Then we can have there this inequality, we got it there. Then ultimately we have taking the exponential on that here, and then we can simplify that everything, it remains there. Finally we have got it this one, and then n we can take it outside of this one, so that n will get it cancelling each other on both sides. So definitely which would have that is the, so by taking the nth root on both sides here, so that we'll get at this term. So that is what we have got it the first term, first equation. And now again we have as n approaches to infinity, so that it means it approaches to L minus epsilon by 2. Since because nth root of an, so as n approaches to 1, as n approaches to infinity and a greater than 0. And also we have that this is L plus m epsilon by 2 power 1 minus m by n, it is also approaches to 1 plus L plus epsilon by 2. For above epsilon greater than 0, there exists a positive integer m1 and m2 such that this is what we have there, these two inequalities. So by taking that maximum among these two, so that we can simplify that on substituting these results in that, here we have got it this relation. Now again we have taken that here, that is the L plus epsilon by 2, that is this relation, as well as L plus epsilon by 2 minus epsilon by 2, and then we have got it this one. So then we have, let us take a P is maximum among m1 and m2. So we have combining equation 2 and 3, so we got it this relation. So now from equation 1 and 4 we have there, so that is the L minus epsilon by 2 power 1 minus m by n, and this should be less than an power 1 by n, and again it should be less than 1 by n, and then multiplied with, it means what this, all these terms should be lies between L minus epsilon and L plus epsilon, so that whatever is this here, so that means what it is sequence n term of that an power 1 by n root there, so that it should be lies between, so that it is what here an power 1 by n minus L epsilon, so that means what, it is limit of an power n 1 by n equal to L. So then similarly we can prove that it is there an by n plus 1 is 0, it is finite. From the case 1 we have that it is again it is a finite, so that it is 0 there, so then it is also infinity. So hence we have proved both the theorem, Gauss's theorem on first and second limit. So converse of the second theorem also need not be true by taking this example there. So that is true for that, because it is, we have got it this two values of this result. So that's why it does not, this limit of an plus 1 by an does not exist. Hence the converse of the Gauss's second theorem on limits need not be true that. So we have discussed here Gauss's first theorem on limits and second theorem on limits that. So these are the references we have followed here in this video. Thank you.